Okay, so as promised, I want to work a few more problems of the type that we were seeing in class the other day. So what I want to do is start with a simple circuit reduction problem, and then we will do a more complicated Kirchhoff's law problem. So we're going to start with a circuit reduction problem that looks something like this. So let's say we've got a system, and I'm just going to make this up as I go here. It looks like this. Okay, and I'm going to label these R1, R2, let's see, we'll do R3, R4, R5, R6, and R7. Okay. All right. And so let's suppose that the question asks, we want to find, let's see, we want to find the current flow through it. And the voltage across each resistor. Okay. All right. So, I need to hook it up to the battery too, don't I? So let's do that real quick. Put that back on there. And then we'll put a battery in here like that. Like so. And we'll call that V1. And we'll say that that's 100 volts. Okay. All right. So the first thing I need to do to be able to do this is to reduce this down to a set or to a single resistance so I can find the total current coming out of the battery. So what I'm going to do is I'm going to look for pieces that are purely in series or purely in parallel with nothing else blocking them. And I'm going to start there. Okay, so when I do that, I see this right here is in parallel. And also this right here is in parallel. Now, you may say, well, but these two are in series. But the problem is they're in series with this combination. The R1 and R2 are in series, but they're in series with the combination R3, 4. So I've got to deal with that first, okay? So I've got to reduce down R3, 4 first, then I can look at the series part of that branch, okay? So since R3, 4 is blocking the branch in a way for R1 and 2, I can't do anything about 1 and 2 yet, okay? So, all right. Okay, so I'm going to deal with R3, 4 and R5, 6. So R3, 4. I've got 1 over R3, 4 is equal to 1 over R3 plus 1 over R4. Now, I didn't give these any values, so let's put some numbers on these real quick. So let's make this one 10, and let's make this one 10, and let's make this one, let's make this one 20, and make this one 40. And we'll make this one 20 and this one 10 and this one 30. This one 30. Why not? Why not? Okay. Okay. All right. So if you, oh, apparently my dog is caught in here. Okay, got my little dog taken care of. She's older and she's having some health issues, I guess. All right, so got those figured out. So what I'm going to do is I'm going to put in those numbers. So R3 is 20. And R4 is 40. All right, so if I get a common denominator here, that would be 40. So 2 over 40 plus 1 over 40 is 3 over 40. So what that means is R34 R34 is 40 over 3. And when we work that out real quick, we get 13.3. Okay. So that means I can replace that R34 combination with a resistor that's equal to 13.3. Now I'm going to go ahead and do R56 also since I'm here. So it's also in parallel. So R56 is 1 over R5 plus 1 over R6. Okay, so that's 1 over 20 plus 1 over 10. Again, get a common denominator. Okay, your common denominator is going to be 20. So you've got 1 over 20 plus 2 over 20 is 3 over 20. Or R, if I take the reciprocal, R56 is 20 over 3. So that's easy enough to figure out. It's about 6.67. All right. So what that means is I can go back to my original picture and I can replace the ones I have circled in purple with individual resistors. So let me do that real quick. So I'm going to just redraw my picture. Ran off the edge there a little bit. Oops. Didn't mean to erase the whole thing, but we'll draw it again. And then we have our battery. Okay, so this was R1, R2. I'm not going to write all the values down again. We can go back to our original picture for that. But I'm just going to replace those parallel boxes with their corresponding equivalent resistances. Now, when I look at this, I can look for other examples of things that are purely in series or purely in parallel. So now I've got these 3 are in series and these 2 are in series, but they are not all in series together because you have this junction here and you have this junction here that messes that up. Okay, so we have to include, or we have to remember that that is part of, I erase my resistors there. There we go. All right. That is part of, oh, I erased my whole circuit, didn't I? Oh, shoot. Let me go back and draw that again. Okay. Learning curve on the iPad, ain't it great? All right, so it would be like this. Like that. Okay. And I'm going to erase that circle and make it purple one. All right, so now I got it. All right, now. Okay, so now what I can do is I can combine R1, R2, and R3, 4 in series, and then combine R5, 6, and R7 in series. Okay, so that's what I'm going to do next. So I've got R1, R2, and R3, 4 together. So R1, 2, 3, 4 is what I'll call it. It's just R1 plus R2 plus R3, 4 because those are in series. Okay, so if I go back and look at my original picture, those first two, oh, I call those volts. I don't want that. Those are ohms. Ohms. Okay, so that's 10 and 10, and then we found that other one was 13.33. So this one's 10, this one's 10, and then this one was 13.33. So the total resistance of that top branch then is 33.3. Okay, the bottom branch is R7 and R5, 6. So those are also in series. So R5, 6, 7 is going to be equal to R5, 6 plus R7. And R7 was 30 and R5, 6 was 6.67. So that's 30 plus 6.67 ohms. So that's 36.67 ohms. All right. Now, so that gets me down to my last combo. And my last combo looks like this, where I just have one resistor on the top branch. I have one resistor on the bottom branch and my battery. So this is R1, 2, 3, 4. And this is R5, 6, 7. And they're in parallel. So this one was 33.33 ohms. And then this one was 36.67 ohms. So since those are in parallel, it's going to be 1 over R total equals 1 over R1, 2, 3, 4 plus 1 over R5, 6, 7. And that's going to be equal to 1 over 33.33 plus 1 over 36.67. And I can do that math real quick. Okay, so 1 over R total is 0.057. So 1 divided by 0.057 then is 17.5. So I've got to flip that over and get 17.5 ohms. Okay, now I need that because I need to find the total current coming out of the battery. So now I'm going to go to Ohm's law. Okay, I'm going to go to Ohm's law. Remember, Ohm's law is V equals I times R if you've forgotten. So I total is going to be equal to V total divided by R total. So that's going to be 100 volts divided by 17.5 ohms. So I total is going to be 5.7 amps. Okay, now what I have to do now is go back and look at my previous pictures. Okay, so I'm going to go back to this first picture here. And I know that I total is coming in here. And it's going out there. But I know it splits up between these two. So I've got part of the current going this way and part of the current going that way. Okay. But since these are in parallel in this last picture, I know the voltages across these are going to be the same as whatever the voltage of the battery is, because it's like they're connected directly to the battery. So we're going to back up to, let's see, this was picture, I think, 3, I think. Yeah. So we're going to call this picture 3. Okay. So we're going to back up to 3. So we know that V567 is 100 volts. Okay. I know that V1234 is 100 volts. So I'm going to use what I know about Ohm's law to solve this problem. So I know that R567 was 33.33. So I567 using Ohm's law is V over R is going to be 100 volts divided by 33.33 ohms. And I'll get that. So that should be about 3. Yeah, about 3 amps. Okay, so there's that one. Then I'm going to go to here and do the same thing. So 1, 2, 3, 4 is 100 volts. Oh, did I get those backwards? I did. Shoot. Okay. That's not 567. That's actually the first one. For some weird reason, I wrote them backwards. So this is 1, 2, 3, 4. So we're just going to switch it like that instead of me erasing everything. So I just got those 2 resistances backwards when I wrote them down. All right. Sorry about that. Okay. So, and then R567 was the 36.67. Okay. So I can find I567. Again, I need to fix that. 1, 2, 3, 4. 1, 2, 3, 4. Okay, 567 is just going to be 100 volts divided by 36.67 amps. And that's 2.7 amps. And that's good because remember, this number and this number better add up to I total, and they do. Okay. All right. So I've got through those branches. Now I can back up and look at picture number 2. Okay. So I'm going to go back to 3 and label those real quick. So this one was 3 amps and this one was 2.7 amps. Okay. So now if I back up to picture number 2, that's what it looks like. So I have 2.7 amps going in this branch, and I have 3 amps going in this branch. Okay. Now I look at these and go, okay, if it's 3 amps, then R1, because it's in series, is going to get 3 amps. R2 is going to get 3 amps, and R34 is going to get 3 amps. And then R7 is going to get 2.7, and R56 is going to get 2.7. Okay. So I'm going to go back down here and say, okay, R1, which was 10 ohms, and I know that I1 is 3 amps. So I can very quickly use Ohm's law to find V1. It's just I1 times R1. So it's 3 amps times 10 ohms, 30 volts. And then I'm done with that one, okay? Because I'm all the way back to an individual resistor. R2 is going to be the same thing. It's also 10 ohms. So 10 ohms. And it still has the same current because that branch is all in series. So it's going to be 3 amps times 10 ohms is also 30 volts. So there's my answers for 1 and 2. 3 amps, go through them, and the voltage drop across each one is 30 volts. But now I've got R34. Okay, R34, remember, was 13.3 ohms. it has a current of 3 amps also. So the voltage across 3, 4 is 3 amps times 13.3 ohms. And that's going to end up being about 39.9. So the reason I knew it had to be about 40 is, remember, the V1, the V2, and the V3, 4 have to add up to 100. So I kind of already knew it was going to be about 40. Okay, so I'm going to stop on that one for just a minute, and I'm going to go to the bottom branch. So R7, I forgot what it was, but let me scoot back up here and look. R7 was 30. Okay, so R7 was 30. And then R56 was 6.67. All right, so R7 is 30 ohms. Because it's parallel, I know, or because it's in series, I know that bottom branch got the 2.7 amps. So its voltage is just 2.7 amps times 30 ohms, and you work that out. 81. Okay, so I'm done with 7 now because it's by itself. So I know its current and its voltage. Okay, but I've still got 5, 6. So I've got R56 was the 6.67 ohms. It also has a current of 2.7 amps. So its voltage is just 2.7 times 6.67. And it's about 18. Okay. Oops, I must have done something wrong on that first one. Okay. So, all right, about 19. And again, I know it's got to be about that because the 81 plus the 19 have to add up to 100. Okay. All right. Now, I'm almost done. Now I've got to back up one more step. So I'm going to back up to number 1. Okay. Where I had those 2 parallel boxes, R34 and R56. Now I know the voltage across them. So I know the voltage across 3 is also 60 because it's whatever was across that combination. And I know the voltage across 4 was also 60. Okay, so now I can find the current. So I3 is just V3 over R3. So that's 60 volts divided by whatever R3 was. And it's been so long ago that we did it, I've forgotten, but we'll go back and look. R3 was 20 and R4 was 40. Okay. So yeah, it's kind of hard to show all this at once. It'd be better if we were on a board, but R3 was 20. So I3 is just 3. Okay. Then R4 or I4 is 60 volts divided by 40 ohms. 1.5. Okay. All right. So that better add up to whatever current we had going through before. Something's wrong. Oh no, I see what I did. Okay. All right. And then R56 is going to be the same. It's going to have the same voltage across it as we found in the previous part. So we found that the voltage across 5, 6 was 19. Okay. So the voltage across 5, 6 was 19. So that means that the voltage across 5 is 19. And the voltage across 6 is 19. And then you're going to find the currents the same way. So I5 is just going to be V5 over R5, and I6 is going to be V6 over R6. Okay, so this is why I redraw my picture so I can back up and see what's hiding inside of each one of those combinations. And I use the rules for series and parallel to remember what has the same current and what has the same voltage. Okay. I think I might have made a little math mistake in there somewhere, but the process should be correct. So you can go back and follow through on that. Okay. All right. So reduce it down to a single resistor, find I total, and then work your way back. All right. Okay. So all right. So I'm gonna now do a Kirchhoff's law one. Okay, Kirchhoff's law is the one where we use the loop rule and the junction rule. So the loop rule said that V net around a loop was equal to 0, and the junction rule said that I net at a junction was 0. Okay. Now, we did an example of this the other day where we just used the loop rule. So I'm going to do one today where we have to use both. So I'm going to draw my picture, and I'm going to draw it big so I can write on it. I'm going to try to draw it big where I can write on it. Okay, so let's say I've got something that looks like this. Okay, so let me label some stuff here. I'm going to call this one V1. I'm going to call this one V2, V3. And then this one's going to be R1. No, I put R2, gosh. R1, R2, R3, R4, and R5. Okay, now, what I have to do first is I have to designate current flow directions. Now, some problems will do this for you. Sometimes you have to do it. You just kind of guess which way the current is flowing, but I have to figure out how many currents I have. So the first thing I'm going to do is figure out how many unique branches I have. So if I look here, this branch right here has no junctions in it. Okay, so that whole piece is going to have its own current. Then this branch right here is kind of the same thing on the other side. It has no junctions, so that all has the same current. And then you've got this middle piece that has a different current. So these three bubbles are going to have three different currents because these junctions here and here are going to force the current to change value. Okay, so I've got three branches and two junctions. Okay, three branches and two junctions. Okay, so the way Kirchhoff works is I need to label my current flow direction. So I'm going to guess, and I'm going to label them in different colors. So I'm going to start with this left-hand branch, and I'm going to say that I1 is going to flow this direction around that branch. Okay, so this is I1. Now notice I don't draw it in the middle branch because when I get those junctions, that current changes. Then I'm going to label the right-hand one with I2, and I'm going to guess that it goes this way, but I don't know. Doesn't matter because if I get it wrong, it'll just be negative. And then I'm going to label I3 as going this way. And I'm just guessing. I have no idea. Okay, I have no idea, but I have to figure out a current flow direction to start with. Okay, now what I'm going to do is I'm going to work around my loops. Okay, I've got two loops, or actually I've got more than two. But I've got a left-hand loop and a right-hand loop. And then if I wanted to, I could go all the way around the outside. But I'm just going to start with the left-hand loop and the right-hand loop. Okay. So I'm going to start with the left loop. I'm going to start in this upper left-hand corner, and I'm going to work around it clockwise. Okay, so I'm going to go this way. Now, this has nothing to do with current flow direction. Okay, this is just you going around and adding stuff up. So remember your sign conventions. Okay, first of all, voltage drops for batteries are whatever side you come out on. So remember, short side is negative, long side is positive. If you need to draw that on your picture, go ahead and do that. Okay. Resistors, you use Ohm's law. You use I times R. Okay. You use I times R if you need to do a voltage drop for resistor. And remember, if you are walking around the loop, adding stuff up in the direction of current flow through the resistor, that's a minus. And if you're going opposite current flow, that's a plus. Okay. So I'm going to start up in the upper left-hand corner, and the first thing I come to is R1. I'm going with the current flow around the loop. So that's a minus I1, R1. Okay. Then I'm going to turn the corner at that gold X, and I'm going to work down that middle branch. Okay. I go through that resistor with the current flow. So that's minus I3, R3. Then I come to the battery. I come in on the negative and I go out on the positive. So that's a plus V2. I get to my bottom junction. I'm going to turn right, and I'm going to go through R5. So that's a minus I1 because it's back to that branch where I1 is times R5. Then I get to my next battery. I'm coming in on the negative and going out on the positive. So that's plus V1. And then I'm back to where I started. So that all equals 0. Okay, so there's one equation that we can use to solve this. Okay, now I'm going to do the right loop. Okay, for it, I'm going to start in the upper right-hand corner because that's what I feel like doing. And I'm going to go counterclockwise just because today that's what I feel like doing. There's no wrong way to do this. Okay, as long as you're starting in the same spot. So if I start that, the first one I come to is R2, but I'm going opposite the current flow. I'm traversing counterclockwise, and the current flow through it is clockwise. So that's a plus I2, R2. Okay. Then I'm going to get to the top junction. I'm going to turn left, and I'm going to go down. So I'm going with the current flow there. So that's minus I3, R3. Then I get to my battery. So I'm coming in on the negative and going out on the positive. So that's a plus V2. Then I'm going to get to the bottom junction. I'm going to turn left, and I'm coming to a battery where I'm going in on the positive and out on the negative. So that's minus V3. Then as I go up this outside right branch, I'm going opposite the current flow again. So that's plus I2, R4. And then I'm back to where I started. So that's 0. Okay. So there's another equation. So I've got 3 unknowns here basically. In a problem like this, you would be considering your current flow to be the unknown. And you would write enough equations to get the number of unknowns solved for. So if I've got 3 unknowns, I've got 3 currents, I need to write 3 equations. Well, I'm out of loops, more or less. So let me do a junction rule. I'm going to do a junction rule for the top junction up here. Okay. So the top junction, and I hope I can get I1, I2, and I3 all in that equation. So if I look at my top junction, all the currents coming into the junction are positive. All the currents going out of the junction are negative. So if I look at this top junction, I1, which is the blue arrow, flows into the junction. I2, which is the green arrow, flows out. And I3 also flows out. So my equation looks like I1 minus I2 minus I3, because in is plus and out is minus, and there's only 3, so it's equal to 0. And there's my third equation. Okay, so the way I would work these problems, or the way I generally put these problems on a test, is I have you set up the equations. I don't try to have you do the algebra, because it's just too much of a thorny thicket to try to find somebody's algebra mistakes. So as long as you can set up an equation like this, with you have to label your currents. Okay, so when you do a problem like this, you need to label your currents yourself. You need to identify the branches like I did with the circles. Then you traverse the loops. You get to decide which way you go, just where, as long as you start in the same place. You decide which way you go around and add things up. And then you write down your equations. Could you go the opposite way? Yeah, and your equations would just be the opposite of mine. Okay, so it's totally okay to do it this way. All right, so that gives you some idea of how to do Kirchhoff's laws.